Now let's come to another property that is quite close to completeness, but not quite the same. So again, let's start with a metric space X with metric D, and then we say that a set M, subset of X, is closed, so that's the new word, if every convergent sequence that has all its elements in M, every convergent sequence that has all its elements in M also has its limit in M. Ooh, okay, let's try to digest this. So convergent sequence must mean convergent sequence in X with respect to X. So there is a limit, but it's probably in X. Let's draw something here. So there is this metric space X, and somewhere inside there is the set M. And there is a convergent sequence that has all its elements in M. So it's full of red points. They all come from the red set M, and it's convergent as a sequence of the metric space. So it has a limit, but possibly the limit could be somewhere in X. Now M is called a closed set if the limit is not somewhere in X, but it is also in M. So you can't get out of M via taking limits. That's what closed sets do for you. They do not let you out by taking limits. Simple example would be, well, you take maybe the interval 0 to 1 in the space X of all real numbers. What do you think? Is it a closed set or not? Can you get out of this set by taking limits of sequences that come from the set? I guess so, because this is not a closed bracket. The interval is open at this endpoint. As I'm saying, is not closed because the sequence xn with xn equals 1 over n is convergent in X, right? It has a limit in X, but the limit, which is 0, is not an element of M, although all of its elements are in M. Okay, so you have a sequence that is completely in the red set and it converges, but the limit is not red, it's outside. So this means it's not a closed set. Another example. Okay, so if we take the closed interval, I mean this name must mean something, from 0 to 1 in the real numbers, then that is a closed set. So you can't get out of that set by taking limits. If your whole sequence is inside the interval from 0 to 1, then also the limit will be part of that interval, possibly at the boundary points, but they also belong to the set M. That's what makes it closed. Now, how is this property of closedness connected to the property of completeness? Let's try to understand this. So closedness versus completeness. So we look at sequences where all elements x1, x2, and so on are in our set M. And then we say that if convergence of the sequence, so if this converges in X, if that implies that Xn converges in M, which means not only the elements of the sequence but also the limit is in M, then M is closed, right? So if you can draw this conclusion, then you have a closed set. Now in contrast, if the property that my sequence is a Cauchy sequence implies that it converges and has its limit in M, then we would say that M is complete. So take a little break and try to understand how the one property is connected to the other. It clearly helps to remember that convergent sequences are always Cauchy sequences, but generally not in the other direction. So we always have this implication. Okay, but not that is telling you the answer. That shows you that if your set M is complete, so this blue arrow holds, then also M will be close to the green arrow holds. How do you see that? Well, to show that the green arrow, the green implication holds, you have to show that convergence of my sequence in X implies convergence in M, but this goes like that. So if the blue arrow holds, then you can draw the green conclusion. Okay, so let's write this down. So if M is complete, then M is closed. Important block. Now the obvious question is, does the reverse implication also hold? So would that also be true? Well, that essentially leads to the question whether or not that reverse implication also holds, and the answer is in general no. Unless your surrounding space capital X is complete. If it's complete, then that implication will hold, and then also that implication will hold. Okay, but in general, not. Okay. So if closedness does not imply completeness, then there must be examples of sets that are closed but not complete. Okay, let's try. So let's take the surrounding set equal to Q, because this is not complete. If the surrounding space were complete, then we would have the reverse implication also, and we could not find counterexamples. So let's assume a surrounding metric space that is not complete. We saw that Q is not complete. And now inside of Q, let's take a set M that looks closed. So let's just take the closed interval 0, 1 inside of X. So let us take the set of rational numbers inside the interval from 0 to 1, including 0 and 1. Is that an example as we are looking for? Well, I'm claiming it is closed. So we have to show that if a sequence converges in X in the rational numbers and has all its elements in M, then it will also have its limit in M. So if the sequence has all rational numbers and it converges in the rational numbers and all its entries are in the interval 0, 1, then also the limit will be in the interval 0 to 1, and as we said, it's also rational, so it will be in M. So indeed, this is closed. Why is it not complete, but not complete? Well, to show this, you just have to write down a Cauchy sequence that has all its elements in M, but not a limit in M. So you could, for example, take a sequence, take a rational approximation of something like pi over 4, which is between 0 and 1. So you could take your x1 equal to 0.7 and x2 equal to 0.78, x3 equal to 0.785, and so on. Make it convergent to pi over 4, which is, well, I'm not sure you have it on your mind. I don't have it on my mind. I have to check it from my cheat sheet here. 539 blah 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 something. Okay, so it is an irrational limit of a sequence that comes entirely from M. So it's not complete. However, we should write that remark down that we made before. So if your surrounding set X is complete, so one of these good metric spaces, and your subset M is closed, then it will be complete. So for M, you have that, for M inside of a complete metric space, you have that closedness implies completeness. And because the other implication always holds, you would have that closeness and completeness are totally the same. Now let me make one more remark. We know some complete spaces. R is complete. It's not easy to show that. Actually, it's part of the definition of the real numbers, and it's that part that makes the definition of the real numbers so difficult. And also things like R2 and so on, or let me just say Rn, and that's why also the complex numbers or Cartesian products of the complex numbers and so on are all complete. So for subsets of R to the power n, there is no difference between closeness and completeness, which is why we didn't experience this difference before, really, because we've only been dealing with subsets of finite dimensional sets like R to the power n, and there is no big difference, or no difference at all between closeness and completeness. This only occurs if your surrounding big metric space X is not complete itself. One more thing that we will need here is the so-called closure. What is that? The closure of a set. Let me explain that for an example. So suppose your set M is the set the interval from 0 to 1, where 0 is excluded and 1 is included in the metric space X of the real numbers with the usual matrix distance measurer. We know it's not closed because you have sequences that go to 0 coming inside of M but leaving M when it comes to the limit. The closure of M is the smallest closed set that contains M. So we write closure of M is in that case the closed interval from 0, 1. That is a closed set now, and it contains M, and it's not bigger than it has to be for these two properties to hold. So in general, you would say that the closure you write close or class M of M, which is subset of X, is the set of all limits of convergent sequences with elements in M. So it's clear that the set M itself is part of the closure of M, because you could look at constant sequences here, just being one and the same element from M, then also the limit would be that very same element, which is then of course still an M. But you could get more than that. Like in the previous example, you could also get the point 0, which was not in M before, but is a limit of a sequence that has all its elements in M. Okay, that this is then automatically a closed set is actually something one has to prove, but yeah, one can do that. So let's just put that down, what we said before. So this is the smallest closed set in X that contains M. Okay guys, I know that was pretty tough, but both closedness and completeness are very important concepts for what is coming. And at least for today, I'm going to promise you that it's not getting any more complicated than it was just right now.